Yeah. All right. So we didn't have class last week. Tuesday was fall break, and Thursday was also fall break if you're me and can't read a calendar. So we didn't have class Thursday either. Um, so got the midterms back. Everybody did pretty good. Everyone seemed to have a pretty firm grasp on what's going on and what we're doing and kind of how everything works. And so I was happy, with how that went. I know I kind of wound up probably a little simpler and a little easier than I necessarily thought going into it, which is fine, because if you really kind of get to the heart of CP, it's kind of conceptually simpler than it sort of looks on the surface, and that's kind of the goal is to figure out the building blocks, right? The barest minimum size of Lego, if Legos still exist. I don't know. At least ones that aren't $500 a box. So anyway, the little like one square with the one little block on it. That's kind of the goal is to find all of those for CV and then understand how we can put them together. And I feel like everyone did a pretty good job of that. So overall, I was pretty happy. Grades are up. Obviously, if you have any questions and talk about anything, email me or message me on Discord. I'm more than happy to discuss the test and kind of how you think you did and all of that good stuff. Um, for anyone who wasn't here before fall break, we were talking about the setup to the midterm. We had a bit of an open discussion about, mostly the career fair and how poorly that went for everyone. And how, it was ultimately pretty disappointing. And so we kind of talked, well, y'all are pretty close to graduating and you're going to be trying to find a job soon. And it's an absolute nightmare because it took me 5 months to find a full-time job, uh, even after working professionally for 15 years. So yeah, it's hard on these streets. All that to say, instead of, you know, a, a big midterm exam and a big final exam, the idea was we're going to do kind of a slightly watered down midterm, and then we'll sort of have a final project where part of the midterm, and I'll send out a little bit more explicit instructions, but kind of the midterm part of the project was just we're going to do some sort of object reconstruction from 3D images because that will bring together everything we've done in 2D computer vision, which is edge detection and feature extraction, which we're going to cover this week and next week is all going to be feature extraction. And then after that, we'll talk about basically doing all of this same stuff just in 3D images and, um, you know, real time. So, like a video or a series of images, some sort of sequential type of thing. But the idea is to apply filtering and then feature extraction to sort of feature recreation. So the idea is if you are walking through a room and you take pictures of all the stuff in the room, you want to be able to then go back out, go back in, and using all of those images, basically extract and determine the size, the shape, where things are in, the scene and the environment you've gone through. And that's kind of the main application of computer vision. What you're going to see a lot of, like all the driverless car stuff, does a whole bunch of structure for motion and image segmentation of stuff I can and cannot run over. So it's kind of a natural extension from everything we're going to end up covering in the class, which, like I said, it's going to be, through feature extraction. And then we're going to kind of go in and look at how can we apply all of these things in a 3D setting or a real-time setting or a real-world application you might encounter, with the ultimate goal being, to have a final project that is good and complicated and well executed enough to put on your GitHub, assuming everyone has one, and if you don't, you really need one. Um, just because everyone you send a resume is going to go pull that, assuming it's one of the 10,000, the one that gets through the ATS. Sorry, I shouldn't be so doom and gloom about the job market. Everyone's going to be fine. Don't even worry about it. Nothing to be afraid of. Just get your own GitHub and put lots of cool stuff in it. And this will be a very nice thing that you can put into a GitHub that you can kind of put on your resume since y'all are so close to graduating. At this point, this being a 400 level class. So that kind of became the ultimate goal. So what we're going to do is there's going to be one more mini project. It'll be just like project one, only for feature extraction. So it'll be, the same setup, 5 or 6 questions where I want you to go in and write out code in a notebook to, do a filtering and an edge detection. And then based off of that, start doing some feature extraction using the algorithms we're going to talk about over the next 4 days. So that's kind of the main announcement. Midterms are done. They were good. I'm going to send out some clarification on the midterm project, but I kind of dropped it in the chat and on the My Courses, but what you do is just go into the assignment on the My Courses page, and you can either just write in a link to the repo or write it on a sheet of paper and send it to me. So I can go and look at it. And the idea is to just sort of set up the general file structure, set up the repo, make sure you've got all the permissions set how you want them. You should probably set it to where you're the only one who can actually write code, and then I can go in and do polls and look at the code and run stuff, but don't make it public and don't make it to where someone can come in and just change code all willy-nilly. So yeah, just set up a repository, give it some file structures that make sense for the project, which is, object recreation for 3D images, and, have a little README in there, if for nothing else, to help you track what you're doing and kind of keep track of like merge and commit messages. And like I said, just drop that in the My Courses. You can either just put it in a text file and upload a text file, or you can actually just type it straight in. So I would like everyone to have that done by the time we come back on Thursday, because it's a pretty simple, straightforward thing you can throw together in about an hour. So that being said, I really hang on 1 second. I got to run grab something. Okay, I'm back. One of the fun things about living in Mississippi is that it was 50 degrees last time. It's like 89 degrees now. So I have to constantly change from heat to air, which, all right. So anyway, that's the midterm project, all that stuff. Next project coming up November, you're going to do same as before, but with edge detection feature extraction. And then we'll have a final exam that's very similar to the midterm, and we'll have, the final project, which is going to be, the big kind of cool, hey, I can post this on LinkedIn and people can come see how great I am, a computer vision type of deal. So what I'm gonna go ahead and do is I'm gonna share my screen, and we can kind of start going through today's lecture. So, all right, let me minimize that. Okay, So we should be able to see a PowerPoint now. I guess just drop a message in the chat if it's not showing up. And we'll walk through this. So we're kind of moving on from edge detection, or not kind of, we are moving on from edge detection to feature extraction, which is the next sort of step up in computer vision complexity and power and what you can do with it. So if you think about it, edges are a feature, and when we apply an edge detector, we're doing feature extraction. It's just that's kind of the lowest level you can get in terms of image segmentation is, you start out by extracting all the edges and you run this edge detector and you come out with your edge image. The next step beyond that is how can I now use the edges to detect other more sophisticated parts of the image, right? If I can isolate and pull out all of my edges, can I then, use how those edges are sort of arranged or where they are in space to do some sort of reasoning about, what's inside the image or what's inside the physical space of which it is an image, that kind of deal. So, we're kind of going from I can pre-process with some filters, I can do some edge detection to pick out my edges inside of a binary image. Kind of once we've done all that, which is sort of just one giant sort of pre-processing data cleaning, kind of step, you can think of it as, right? Once we get to that point, then how do we kind of start doing good, useful stuff with computer vision? So, outline for today, just a quick review. We've already kind of gone over all of this, but everything we've talked about before now is essentially, taking an image and using a bunch of tricks from our tool bag to get it to a place where I can start pulling features and doing reasoning and making decisions about kind of the world the image has captured. Um, so now with feature extraction, we're kind of taking that next step, and we're going to talk a little bit about just sort of what does that mean. It means what it says, it's feature extraction, but there's a little more to it we can kind of say just within the confines of computer vision. And then there are three sort of big popular feature extraction algorithms that you will see used consistently in pretty much any computer vision project that involves segmentation and extraction. So the three we're going to cover is the hue transform, which is kind of the lowest level of feature extraction. It's kind of like a slightly better edge detector. You can kind of think of it as. And then there's SIFT and SURF. Those are algorithms that are also for feature extraction. They're a little bit more advanced than just a hue transform. And SURF is just a more computationally efficient but slightly less accurate implementation of the SIFT algorithm. So we'll kind of cover those both at the same time, and we can, as we're doing that, sort of discuss the trade-offs between if you want to run SIFT, which is better, or if you are under some sort of constraint, such as a real-time constraint, you would use SURF, and sort of how you balance that between the two that work the same way. One's just faster. And then the last one we'll talk about is YOLO, or You Only Live Once, which is sort of the baseline for machine learning models or any sort of higher level reasoning about an image. So those are the three we're going to cover because they're, like I said, they're the three most popular. If you talk to anyone about computer vision, they're going to ask you, hey, what's a hue transform? When do you use it? Those are the ones you get asked about. at least in my experience. So this just kind of goes over everything I was just saying. You know, we've gotten to edge detection, which is sort of the lowest level you can kind of get in terms of looking at an image and extracting features. So we want to take everything we've kind of learned up until now to create a better algorithm to operate on an image. And our goal here is to, again, like I said, extract features. So we want to know what is inside the image and can we sort of separate everything from each other and figure out, you know, what everything is. So here's kind of the definition of feature extraction. You know, you're finding and isolating a pattern or some particular kind of information within the video that can be used for further analysis. So that is the biggest thing about feature extraction versus everything we've learned so far, which is that when we get to edge detection, right, we're not really doing anything with that other than drawing lines and saying we know where straight lines are in the image, right? We can't just look at an image that is the output of an edge detector and do any sort of analysis on it outside of just some very basic things. Like that's, we have to go kind of one step further if we want to do any of the important stuff like recognizing objects or classifying objects or detecting things, you know, like we want to go from getting to an image with edges picked out to, you know, finding faces in a video feed, right? Before we get to that point, we've got to kind of figure out the edges, filter out what's the face and what's not the face, find kind of the shape. But then if we want to go in and actually determine, is it a face? As an example, then that's kind of where we have to take this next step into feature extraction. And so if you think about this in terms of the example we've seen over the last few lectures where we looked at, you know, an edge detection algorithm for a classroom, you know, the edge detection shows us where the lines are, right? That's kind of the simplest feature we could possibly extract. And, you know, we want to look at this and say, okay, well, you know, based off of this, can I pull out and label everything that's a desk, everything that's a chair, and everything that's floor, right? I've got my edges. How can I now extract the different objects inside of that image in a way that will give me important information like where's a desk, where's a chair, where's the floor. And we kind of talked about this several times. You know, if we were going to do some sort of task like walk from the door to a chair, we would need to know, well, you know, where's the floor I can walk on? What is a table I can't walk into or through? And then what is the chair? And so the edge gives us this where all these lines are. The next step is to use some sort of feature extraction to then pick out all of each kind of thing inside of the image. And so I touched on this real briefly a minute ago, but in general, you can sort of break down an image into three types of features. And we're going to, the algorithms we're going to look at operate at different levels. So like I said, the lowest level features are going to be the features you can determine from what's inside the pixels, essentially. It's kind of the lowest step of feature extraction because it works the most directly with sort of the internal information within a pixel. So we're still looking at pixels as sort of their own discrete thing with their own discrete values that we can figure out how those relate to each other. And what we do with the hue transform is then take that information and try to make decisions about small regions or local areas within an image. So that's what the low level feature detection, we'll be doing that with the hue transform, which is basically an edge detector that you then use a much more complicated convolutional kernel to find discrete shapes. Um, and that's our low level one. The mid level, where you are detecting more complicated things, like instead of walking through the steps the hue transform has to do to get at geometric shapes, you can do it at a higher level without having to necessarily touch and transform every pixel. And then kind of the high level is when you're working with features that represent a complex object, right? So we're not at that level, and what YOLO does is you're no longer looking for lines or shapes. You are looking for abstract or complicated features. With low level, you're essentially telling the hue transform how to go find lines. At the high level, what you're essentially doing is telling the algorithm to go find people. And that's kind of the high level feature extraction. And YOLO and the other algorithms you see are typically when you get into the machine learning part, because that's where the algorithms come in that you use to train a model to detect, people or cars or whatever. And so, kind of like what we've done so far, feature extraction is the same, where you start at this, very rudimentary level of how can I just find shapes based off of my edges. And then you kind of have your mid-level where it's like, well, how do I determine if this shape is a ball or the moon or the wheel on a tire, something like that. Okay, I've got shapes, but what can I reason with about what those represent? And then you've got kind of the highest level, which is, hey, I need to see all the faces. And what you will see at the high level of feature extraction that we won't cover in this class, but that is, an interesting application that involves both computer vision and machine learning that if you are interested, you can learn a little more about. But that gets to semantic algorithms, which is basically you just type in go find faces, and the algorithm will then do all of that. It'll take care of all of this stuff, all by its lonesome, where you're not really having to interface with code at all. You can really just give a semantic construction and get an output. And that's been really interesting to see develop, because we couldn't do that when I first started working on these things. And now, it's really interesting because you could tell, a driverless vehicle, you can tell it things like, turn left at the yellow fire hydrant. And that will make sense without having to program in, this is how you find a fire hydrant, this is how you find its color, this is how you find how far away it is, and this is how you actuate the wheels to get around it. So it's really cool stuff, and it's progressing pretty rapidly. Yeah. So these are the type of features we're going to look for. So the first thing we're going to do is this low level feature extraction. So we're looking at the lowest level we can get to, which is that first step up the ladder of, I don't want to find just lines, I want to find shapes. So the way we do this is we start from the edges, and then what the hue transform does is try to find a way to turn an edge into a shape. And so thinking about this, from that lowest level, it's my building block. Where do I go from here? The idea is we want to find the shapes. Then if we find the shapes, we can say, all right, well, the feature I really want to extract is a soccer ball. So the very first thing I have to do is find all the circles in the image. So, if you're watching a soccer game and they have, the tracker that is following the ball around, or, a lot of stuff in football where you see they're kind of marking where something is happening, stuff like, even stuff just like where the first down line is, stuff like that. That all starts kind of from here, where if I want to be able to follow a ball as it's moving across the field, before I can do anything else, I have to figure out what's field and what's ball. And the first step in doing that is to just find all the circles. And once you've found all the circles, you can move up the sort of feature extraction ladder to, which circle did I find that has the pattern or texture I would expect to find on a soccer ball, and kind of go from there. All right. And the way we are going to do that is with the hue transform, like I mentioned. Uh, and kind of like I mentioned, this is sort of the most popular algorithm for extracting shapes. And like I said, it's edge detection with extra steps. So when we detected our edges, we used convolutional kernels to kind of average out all of the pixels and see which ones were next to each other in a straight line type of fashion. And we had a convolutional kernel to find vertical lines, and we had a convolutional kernel to find horizontal lines, and we could, if we tried really hard, come up with a sort of acceptable way of finding curves, which is kind of what the hue transform adds to edge detection to make it a shape detector. Is after the convolutional kernels sort of have their pass at it and the edge detector, then we apply a much more sophisticated version of a convolutional kernel to pick out of all of the edges, which set of edges is a unique, discrete shape. All right. And the way we do this is prior to now, all of the transforms we've done, you can sort of equate to, a transform in some sort of coordinate space that sort of maps to a real thing, right? And what I mean by that is the other transforms we've done for color spaces like HSI and sort of the custom ones everyone did on Project One, were basically taking the values of a pixel and changing them to other values that are still in that pixel, but we have still sort of stayed within the coordinate space of the pixel. If it's three colors, right, or if it's binary, we can go from binary and grayscale back to color, right? Everything we're working with when we look at these transforms is a value inside of a pixel, not a value derived from what is inside of the pixel. And so what that means is hue space is not a Cartesian space. It is a parameter space. So kind of what I was saying there is it's not, hue space does not represent a place in the world or a location of a pixel. We can plot and look at the HSI color space, or, we can plot and look at a binary image, right? And so we can see what the transformed pixel looks like. Basically, we can still render it as an image. Um, that is not what the hue space is. Hue space is a parameter space, which is parameters derived from what is inside the pixel. So instead of assigning some version of a location of a pixel value through a hue transform, we are giving each pixel a parameter that is derived from the pixel values, that is just kind of a number that is a measurement of something about the pixel. And the way it's done, I'm not going to get all the way into the math stuff like we've done with the others, just because it's harder and it's math enough to be outside of the scope of what we want to do in this class. But essentially, what a hue space is a measure of if a pixel falls within the bounds of the equation of a line, so x plus slope, right? If it is within some bounds of this relationship between x and y, then it is within some amount of being a line, right? So it's pretty much just that. It's going into an edge image, an image that's already had an edge detector run on it, and it is looking at every pixel and calculating, a slope of a line equation, basically, and then saying, okay, well, how close is this to a line? How close is it to matching everything around it in terms of a line? What you'll see is uh, you can get an infinite slope essentially with this equation based off of how it is. That is a giant spider, you buddy. Um, so our workaround for that is to convert to polar coordinates or a polar coordinate parameter space, right? Because we still want to remember we're working with parameters and not actual values from the pixel. So we use these polar coordinates. You can see you've got essentially the distance from the origin to wherever that line is, and then the degree to which it is perpendicular to the x-axis. Um, and you can do this the other way and measure if it's perpendicular to the y-axis. It's an arbitrary choice, but everyone uses the x-axis. So if you want to use all the free stuff and already made algorithms, you're kind of stuck doing that. Real quick though, who wants to see this giant? Oh, he's under the couch now. Bye, spider friend. Be nice to spiders. They kill the stuff that actually hurts you. All right. So our question ultimately in a hue transform is based off of the parameters of this pixel. How well does it map to a continuous line? So the way it measures that, like I said, we're pretty much doing a second type of convolutional kernel that is just a lot more complicated and a lot smarter and a lot bigger because the accumulation matrix is essentially the same size as the image versus like a 9 by 9 window. We are kind of accumulating everything in the image. So the matrix is basically the size of the image. But what it does is it uses a voting system to assign shapes. And what that means is it goes into an edge image, looks at all the pixels after converting them to hue space, and then figures out based off of a voting process which edge does that pixel belong to. And once we figure that out, we want to measure how closely do the features we find in the accumulation matrix and hue space relate to a line or a circle, pretty much. And then which lines and circles are connected inside our accumulation matrix, telling us it's part of the same shape. So it basically, we have our first convolutional kernels in the edge detector that, get to decide what is and isn't an edge. And the accumulation matrix and the hue transform is just a really, really fancy convolutional kernel that then gets to go in and decide which edges are grouped together as a discrete shape within the image. And that's obviously that's why we start here when we start talking about feature extraction, because it is just an edge detector and then another convolution to turn edges into shapes. So what we're going to do is we're going to walk through an example, and I'm going to kind of talk through this, and then we have some code we can run to go through this. But the idea is you've got your step 0. So I've got my image. Before I do anything else, if I want to use the hue transform to do feature extraction, I have to turn it into an edge image. So if we go back to our example here, um, it also kind of helps to think about it this way. You can detect the edges in a regular image, right? I can apply an edge detector to an image, regardless of whether or not it's been filtered with like a low pass or high pass or Gaussian filter. Whether I filter it or not, I can still apply the edge detector and I can still get this result. Obviously, whether or not I do some filtering first is going to determine how good the edges are, and we've covered how to choose that filter. So we've kind of got everything to get to here. The point is, I can do edge detection on sort of any image. I can only do a hue transform on an edge image, right? If I give it an image that is not a binary yes or no, this is an edge, um, then it won't work, right? So that's just another thing you got to kind of keep in mind with this in particular, with the hue transform and everything going forward, right? Everything we've done till now, you can just do to an image. Everything we do after this is going to start from an edge image or the output of a hue transform, which also has to start from an edge detector, which is why it's such a seemingly simple algorithm that we spend so much time on, is because it's the first thing we do when we want to do more advanced computer vision. So the first thing I have to do is I have to give it an edge detected image. So I have to go in and detect the edges in my image first. So that's why we've got our step 0 is we need to apply an edge detector. I've got an example in a Python notebook we're going to run through. And in that, I'm using the Canny edge detector. You can use anyone you like. People basically default to Canny edge detection. So if you do go out there and find other people's work, or more advanced forms of the hue transform, you will almost always encounter the Canny edge detector first. That's just kind of, like I said, the default choice, how textbooks do it, how tutorials do it, how we're doing it. It's just the easiest place to start because it's advanced enough to do a good job without requiring you to do just a whole lot of tweaking or processing, because at this point you just want good edges. You don't really care how you get there or how good they are as long as they are good enough. Um, so you do edge detection and you end up with a binary image, which is the other important thing about the hue transform is it only works on a binary image. You can't apply it to a color image and you can't apply it to a grayscale image. You can only apply it to, like I said, the output of an edge detector that is essentially either black or white, edge, not edge. Um, and so once we give it that, right, we apply our Canny edge detector and we have our XY location and a value of 1 or 0. We, like I mentioned before, we convert that to polar coordinates. Just like up here, right? We could do linear, we could do good old junior high mx plus b, but lots of funky things can happen with the slope when we do it this way. It can be, infinity. Stuff can happen with the y-intercept where it wanders away from zero depending on what you do. So for the sake of not getting runtime errors or getting not a number, which you guys may have never encountered NAND, but boy, did they used to be a thing. But anyway, just to avoid any sort of gotchas, we turn it into this polar coordinate. Like I said, which is, the distance from our origin, so the distance from 0, 0 in the image to where the point is, which is just a singular value of a distance. And then the angle is the angle from the y-axis. So it basically it is what it is. It's just turning a 2D Cartesian space into a 2D spherical space where you're just measuring a distance from the origin and an offset from an origin. So we have put this into, our polar coordinates where we want, and that's kind of, what I mean about how we're now in a parameter space, because we're not looking at what is inside the pixel. We are looking at where the pixel is located within an edge. So that's kind of its derived parameter. And so if we're looking for a line or any kind of shape in a 2D image, what we're going to do is the accumulator matrix, which is our convolutional kernel, but better for lines. So if I want to find a square or a triangle or a rectangle, any sort of 2D straight line shape, then I can just have a 2D accumulator matrix where there are two dimensions, which one dimension is for R, one dimension is for theta. So I've turned a pixel at an XY location into just a R value and a theta value, which are the two derived values after the hue transform. So I have built my accumulator matrix with two dimensions, and it's looking at the R and the theta for each pixel. Because we have already built it in a way where it can safely assume that the pixel is a 1 or a 0. And it can safely assume that the pixel is already part of an edge, right? I can't find an edge with just R and theta if I haven't, already put the edge there to begin with. And that's why, right, none of the edge detectors we looked anything like this, because they create the edges, and then this kind of doesn't look like any of the edge detectors because it finds shapes based on edges. All right. So we have our 2D accumulator matrix. What we want to do is we use our binary image from step 0, and it's called an accumulator matrix because the values of the edge are used to increment how much the subsequent pixels belong to that edge as a self-contained line. So it's a little confusing conceptually, but what you can do is you can think of it as we overlay this accumulator over the image. And essentially what it does is everyone in the matrix gets a vote as to whether or not a pixel is on a self-contained line. So when you put the matrix down on the image, all of the cells around that point basically get to say either, yes, I think this point is part of the line I know I am on, or no, I do not think this point is a part of the line on which I am. So it kind of works with the voting is the value of each cell goes up the more pixels around the one you are looking at think, within the internal mathematics that they are related and together within this discrete shape. Um, and then kind of the last thing you do once you get here is you detect peaks. I gotta step away for 1 second before we get to the notebook. So just pop over here real quick. Um, okay, so that's the last step is detect the peaks. So what we want to do is I've got a matrix and each value contains some amount of votes as to whether or not it is part of a shape. And all we do at that point is look across the matrix and decide how many votes it takes to be a part of that line that is a part of that shape. And we can do that, with a thresholding where we basically say for a pixel to be a member of this line, it has to have so many votes from the adjacent pixels. So in, the convolutional kernel sense that we're used to, it's sort of the same thing where we're taking all of the pixel values in our 3x3 window and then accumulating them basically in some way where the adjacent 9 pixels kind of get a say in what our center pixel that we are looking at becomes, whether or not it's an edge or not, or how it gets smoothed or blurred. It's the same concept with all of the adjacent pixels are kind of getting a say in how the one we're looking at is represented post processing. The hue transform is similar, conceptually and much more complicated mathematically, but it's still the same idea as, all of the adjacent pixels get a say in whether or not they think this particular pixel is, their neighbor along this line or not. And then, we threshold it and we look at the peaks, and wherever we find a peak, we can say that is part of this line. And once we have that, then we can, soldier on with our cool, more advanced feature detection. And so the last thing I want to do today is go through a Python notebook to kind of show some of this. So let me restart, clear all outputs. So probably from this point forward, nothing's going to be done by hand like we've done before with the transforms and some filters and edge detection where you kind of went in and touched the actual math. From this point forward, since we've already kind of built the building blocks, I'm going to stick to OpenCV libraries or other different libraries because I feel like, at this point, we all know enough of the nitty gritty. So what we'll do is, I should be here. Okay. What we're going to do is we start with all our normal inputs, right? And then we want to just go in and, for our first time when we're looking at it and want to know sort of how everything's working, we're just going to make our own simple binary image and draw some lines. So, I'm using my image, I'm using NP zeros. I've declared the type, so I won't get any runtime errors because knowing the type of things is what we're good at as computer scientists and other people can't do. So we did that, simple things, super important. And then we draw some lines. You can see there are just some line equations. And then we're going to apply the Caney edge detector with just some, simple parameters that we're not going to bother with too much. We just want to get an edge image out of this. So what you can see is up top, that's the image we created. Is just a square with a line through it or two triangles, whatever you want to call it. And we run the edge detector. And because we know a lot about edge detectors and how they work, we understand why there's a little space and then another line, other two lines, because the way the Canny edge detector works, it basically doesn't see thick lines because of the way it does, the Gaussian blur and the gradient. It sees a thin line and then stuff that isn't changing enough to be a line and then another thin line, right? And that's kind of why we go through all of this stuff to get here, is because we know why the edges look like this and we know why we don't still have just a square with a line through it, because that will impact everything we do from this point forward. So that's our edge detection, right? We built the stop image, we detected our edges in this bottom image. So now I have my binary image with lines in it, right? I've got my 1, 0, am I aligned? Where am I? And the arrangement of pixels in the image. So what we're going to do then is just throw up the Q lines from OpenCV, right? We're not going to go in and change every X, Y into an R theta. We're not going to go in and write an accumulation matrix. We've officially graduated to just making OpenCV do it. So this is our lines. We've got pi over 180 for our theta, and we've got 1 for our r, and we're going in and finding all of these things. And then the last number, the 100, that's our threshold, which is just the number of votes a pixel has to have to become part of a line in the hue space. And what we're going to do is just display the image after we've gone in and detected all the lines. We're going to draw the lines on the original image. And you can see we've got, this code that's giving us our A, our B, our thetas, our X positions. We're just kind of letting all of this happen without us having to bother with it, because what we're really doing is just going from the lines that the hue detector gave us to lines we can easily draw, and then we're going to look at the outputs. So we've got the original image, and then we have the results of the hue transform, which are bad, right? It's found two straight lines kind of in the bottom right corner of the image, which is, wildly incorrect. So, we got to kind of figure out, based off of what we know, why do we think, um, we got this crummy result. And what you think of is that the threshold has been set way too high, right? The number of votes each pixel needs to belong to a line is so high that it's only finding a couple of them. And that's because if you look here, we've got our threshold is 100. And our image is 200 by 200, right? So the odds of any one pixel getting 100 votes, or a fraction of 100, I don't think it's exactly 100. I think it's more of a 10%. I'm not entirely certain, but whatever it is, we've got a 200 by 200 image that we're trying to threshold at 100 votes. So there's no way this is going to be able to work based off of those parameters. What we can do is come in here and tinker with some of the OpenCV settings that we need to understand how work. And because we've kind of gone everything to get up to this point, we now can understand that, if we drop the threshold by half, so pixels only need half as many votes to become a line, and then we can also add things like line length and line gap, which are exactly what they sound like. It's essentially saying when you go find the lines, if any line is less than 20 pixels long, throw it out anyway. That's not long enough. It's probably noise. We don't care about it. And then we can set the next line gap, which is essentially how far away can 2 pixels be uh, before they become two lines instead of members of the same line, right? And so these are just some of the parameters we can mess around with. There's more, there are more advanced hue transform options in OpenCV, but for us, when we just want to understand kind of at the lowest level how it all works, this is what we need is we understand what the threshold is and we can understand line length and line gap. It's not something when we want to do a hue transform, we have to just change numbers at random because we're not really sure what's going on. We understand the parameters, we understand how they work, so we can make informed decisions about how to set those parameters to try and get what we want, which is a proper hue transform. What you see at either end of the diagonal line, however, comes from all the way back up the output of the canny edge detector. So if you look, because of the way the lines are, there's this little bitty curve right here where these two lines are just a little bit farther away from this corner than all of the other lines are, which means when we run the hue transform, those teeny tiny areas that were further away from each other because of how the lines were detected, those don't show up inside of the hue space and the hue transform, which again is just why we learn all of this boring stuff to get to this point, is so that not only do we know why these gaps are there, we know how to resolve that, versus what some people do. A lot of people who haven't had like a computer vision class that still have to do some sort of image processing, you know, what will happen is you'll get to this step and you'll not really know why there's dead space. And so, I've seen people do a lot of things like where you just keep changing these numbers until it looks better or you cannot see the dead space. Or if you come up here to this, you'll see people also just start changing those numbers sort of arbitrarily until you don't have this tiny little gap at either end. And so knowing how this works and what all the parameters are essentially saves you hours to days worth of manually and randomly just adjusting parameters to try and get things to work. And I know people do that because I did that with the first lane detection algorithms I wrote back when I was working on driverless vehicles, because I came from a physics background initially and had never encountered any of this. I'd never seen any of this theory before. So as a physicist trying to write code to teach a vehicle where the sides of the road are, and I'm wanting to find lines, I'm kind of hosed. I don't know the theory. I don't know what to do. I just keep changing parameters till it looks good enough to make a video for a slide to show a kernel that makes it look like we know what we're doing when really it's just kind of ham-fistedly changing numbers to make something look pretty, which is just exactly not what you should do and not what y'all should be doing, because we're taking so much time to learn the theory behind all the things and how they work and why, which like I keep saying, it's going to make you better at this than someone who has not seen this material. This is one of those things where as you graduate and go out to the world, right, you want to know what are the things sort of only you can do that other people can't, or what makes your degree special over someone else's. And this is one of those things, right? If you are going up against someone from an engineering or, like me, a physics background who wants to do heavy duty computer vision work, you will have an advantage over those people, and you will know more, and you will have something that you are good at because of the choices you made in your education. So that's all we'll cover for today. What we'll do, Thursday we'll talk about Sift and Surf, and then next week we'll talk about YOLO and kind of some of the other stuff you might encounter just in terms of algorithms that are out there in the world. Um, so that's the plan for the next couple weeks, and then what I'm going to do is, give away the biggest secret for everyone working in sort of any sort of engineering field, especially anyone teaching classes like that, is, ChatGPT could just write all of this essentially. And so, you can go in and say, okay, I want to do a Hue transform and I want to just do it on a really simple dummy image. And then if I know what all of these things mean and how all of these things work, then I can fix any problems that I see off of any sort of, generative AI code that's been written. And that's, another thing that, gives you a leg up sort of in the world is that, you can read the code you get from a Gen AI and know what is wrong with it and know, what will happen because of the things that are wrong with it. Right. So the first time we wanted to do this, right, we used let me come back over here. Right. So the code that came straight out of ChatGPT gave me this crappy result, right? But because I know how everything works and why it works the way it does, then, it's not hard to go in, fix the thresholding parameters, or fix how the edges are detected to then get, a better result without having to kind of write the boring, dumb import file IO images in the right format, all of that stuff. Or, if you want to ask, hey, what library is best for a Hue transform? That's all stuff you can and should get from Gen AI because why wouldn't you? It's there, it's efficient, it's fast. It would have taken considerably longer to write all of this from scratch. But, I can get something to work with the outputs of Gen AI. It is then my responsibility as the coder to know how to fix what ChatGPT gave me because I know how the algorithms work. And, if you work with it enough, you start to figure out how Gen AI works and what you can and can't ask it, which is, something I'm kind of encouraging you guys to go find out as well. What how do I can get here if I want to use generative AI, and that's fine, but I have to know all of this stuff and all of the edge detection stuff to get here. And once I'm to here, there's no way a generative AI is going to figure out for me how to get rid of the dead space, right? That is specific enough and hard enough that the onus is on me to be able to fix it, right? I can go from totally crappy to acceptable, but to make it worthwhile and useful, it's still up to me to know why it misses those pixels and how to change the edge detector, change the thresholding from the Hue transform to fix it. So, yeah, I really wanted to show that. I try to show that to everyone in every class of, what you can get and what you can't get and why you still have to know things. Um, for computer vision. So that is everything I had. Let me stop sharing. I'd show everyone the giant spider, but he's still under the couch. So unless anyone has any questions, what I'll go ahead and do is stop the recording and end class here. So looks like there aren't any questions. All right.